All right, let's jump right in. Today we're looking at a pretty audacious claim. The idea that a mathematical problem, one that's been considered unsolvable for 200 years, might have just been cracked. We are talking about the hunt for exact answers to some seriously complex equations.
You know, the source material starts with this quote, and it really sets the tone, doesn't it? Limits exist only until they are surpassed. It's the perfect way to frame what we're talking about today, which is all about pushing up against a boundary that's been accepted for centuries and asking, hey, was that limit real, or was it just a roadblock we hadn't figured out how to get around yet? Okay, so first things first, let's get some context. To really get why this new claim is such a big deal, we have to understand the massive wall it's up against. We're talking about a mathematical barrier that's been standing for 200 years, defining the very limits of algebra.
So check out this timeline. It really tells a story. For centuries, mathematicians were on a roll, right? They were just knocking down these problems one by one, solving equations of degree 2, then 3, and then all the way back in 1545, degree 4. It seemed like nothing could stop them. And then, bam, 1824, the Abel-Ruffini theorem just slams on the brakes. It basically declared that a general formula for anything degree 5 or higher was impossible. Galois theory came along and doubled down on that. And for 200 years, that was it. Case closed.
Now, we need to be super clear about what unsolvable actually means here. It's a specific thing. It means you can't find a solution in radicals. Think of it like this. You probably remember the quadratic formula from school, right? A single, beautiful formula that can solve any quadratic equation you throw at it using just basic math and square roots. Well, unsolvable meant that a formula like that just didn't exist for equations of degree 5 or higher. That's the problem that was considered impossible to crack. So, where does that leave us today? Well, for 200 years, everyone just worked around this problem. They used computers to get close enough answers, approximations, but they accepted the limit. And that brings us to the present day and a direct challenge to all that history from Professor Murad Sultan Ezouidi.
And here is the core claim right from the source material. It's pretty bold. The claim is that not only can you solve these higher degree equations, but that a complete, exact, symbolic solution has been found for a 7th degree polynomial. And let's be clear, we're not talking about a close enough computer guess, we're talking an exact answer. This flies right in the face of what the Abel-Ruffini theorem has said for centuries.
I love this quote from the author because it really gets to the why behind this whole thing. He says, I have never accepted that limitation. The argument here is super interesting. It's not saying those mathematicians from 200 years ago were wrong. It's saying they were working with an incomplete toolbox. It reframes the whole idea of impossible from being a fundamental law of the universe to just a limitation of the tools they had at the time.
So, you're probably asking, okay, how is this even possible? Well, the source argues it's not about tweaking the old methods. It's about throwing out the old playbook and writing a new one. This new approach, called Ezouidi's theorem, is a really sharp break from the way things have been done.
And this table does a great job of laying out just how different the thinking is. You've got the classical methods on one side saying, nope, impossible after degree 4, and Ezouidi theorem on the other saying, actually, we can get exact symbolic solutions. The whole theoretical foundation is different too. Instead of field theory, it uses something called recursive discriminant structures. And this last part is key. Instead of relying on approximations, it claims to be 100% algebraically verifiable. It's a total rejection of the idea that there are some problems we just can't solve.
Okay, that phrase recursive discriminant structures sounds pretty intense, I know. So let's break it down without getting tangled up in these super technical details. The source basically lays it out as a 3-step process. You start with the basic numbers from your equation, you apply some special transformations, and those transformations systematically lead you to the exact roots. It's a new kind of machine for finding the answer.
So, what's the big takeaway? Why does this matter? Well, if this claim holds up, and that's a big if until it's been fully peer-reviewed, the implications are frankly huge. This isn't just about solving one tricky math problem. It would be about completely redefining the boundaries of what we thought was possible in algebra.
And the real magic, according to the source, is how it gets around those old roadblocks. It claims to bypass the very group theory issues that stumped geniuses like Galois. It delivers exact forms, not just close enough numbers. And it offers a universal recursive formula, maybe one that could work for any degree, which would be an absolutely massive expansion of algebra's toolkit. You can really feel the ambition in this quote from the source. It calls this the rebirth of algebraic solvability. See, this isn't being framed as a small step forward. This is presented as a complete revolution, a rebirth of the belief that we actually can find perfect, exact answers for these huge, messy problems.
All right, enough with the theory and the big claims. Talk is cheap, right? The source material puts its money where its mouth is with a concrete example. So let's look at a real, gnarly, seventh-degree polynomial, the kind of thing that for 200 years everyone agreed was impossible to solve for an exact answer. And here it is. Just take a second to look at that thing. I mean, it's a monster. It is complicated. It is intimidating. And this is exactly the type of problem that traditionally you'd feed to a supercomputer just to get a decimal approximation. The idea of finding a simple, exact answer in there, it seems, well, impossible.
Okay, so this is the payoff. The source takes this massive equation and runs it through the new theorem. And the big question is, after all of that, what is the beautiful, simple, exact answer that pops out for one of its roots?
The answer is 4. That's it. Not 4.0001 or some endless string of decimals, just 4. And get this, the source says this root has a multiplicity of 7, which is just a fancy way of saying that this one simple number, 4, is the answer for all 7 roots of that insanely complicated equation. Wild, right?
And this comparison just says it all, doesn't it? On one side, you have this absolute beast of a problem, a total wall of numbers. And on the other, you have a solution that is just so simple and elegant. This is the whole point, right? To show that this new method can supposedly cut through all that chaos and find the perfect, simple order hidden inside.
So in the end, looking at Professor Ezouidi's work leaves us with a really provocative question. Now, whether this theorem gets accepted by the whole math community and becomes the new standard, well, that remains to be seen. But it forces us to ask something bigger. If a wall that's been standing for 200 years in mathematics can be challenged like this, what other impossible walls out there in all fields of science are just waiting for someone to come along with a new way of thinking and knock them right down?